All right, welcome to this explainer. Let's jump right in and explore the fascinating physics of how and why literally everything in our universe moves. I mean, from giant massive planets revolving around the sun to a tiny pendulum swinging back and forth, motion is absolutely everywhere. It's the essential first step to unlocking the rest of physics.
But you know, before we get completely lost in the math and the graphs, ask yourself this. Are you truly sitting still right now? Think about it. Even if you were perfectly frozen in your chair watching this, you're still on a planet hurtling through space, right? And that brings us to a fundamental truth about our universe. Everything around us is either at rest or in motion. But as we'll see today, it is all a matter of perspective.
So, here's how we're going to break this down today. First, the basics of motion. 2. Distance versus displacement. 3. Speed and velocity explained. 4. Understanding acceleration. 5. Visualizing motion with graphs. And finally, 6. The equations of motion.
Kicking things off with Section 1, the basics of motion, finding your footing.
Okay, so the absolute most crucial thing to grasp here is that motion is simply the change in the position of an object over time relative to a specific reference point. It is entirely relative. Imagine you're sitting on a moving train. To the person sitting right next to you, you're perfectly stationary. But to someone standing outside on the platform, you are zipping by. So to accurately describe motion, we always, and I mean always, have to define a specific reference point first.
Now, once we have that reference point nailed down, we can categorize motion into a few distinct types. You've got rectilinear motion, which just occurs in a straight line. Circular motion follows a circular path, while rotational motion spins around a fixed axis. Then there's oscillatory motion. Think of the repeated to and fro swing of a pendulum. We also see periodic motion, which repeats after equal intervals of time. And of course, random motion, with absolutely no fixed path or direction. But for today, we are going to focus heavily on motion in a straight line.
All right, moving on to Section 2, distance versus displacement, getting from A to B.
This is a brilliant contrast here that trips a lot of people up. Distance is exactly what it sounds like, the total length of the actual path traveled by an object. It's a scalar quantity, meaning it's just a number, and it's always positive. Displacement, however, is a vector. This means it only cares strictly about the absolute shortest, straight-line distance between your exact starting and ending positions, and it includes your specific direction. Displacement can actually be zero, even when your distance isn't, and it can literally never be greater than your total distance.
Let's visualize this. Think about an athlete on a straight track. Say they run from the starting line, point O, all the way to point A, 100 meters away, and then they turn around and run back to point B at the 40-meter mark. Their total distance just keeps adding up. They ran 100 meters plus 60 meters back, covering a total distance of 160 meters. But their displacement, it's just that shortest straight line from the start to where they are right now. That's just 40 meters. If they ran all the way back to the starting line, their displacement would mathematically be zero, even though they physically just ran 200 meters. Wild, right?
Let's roll right into Section 3, speed and velocity explained, pacing and direction.
Just like our last comparison, these two concepts get mixed up all the time in everyday conversation. Speed tells us how fast an object moves. It is defined simply as distance traveled per unit time. And like distance, it's a scalar quantity. You calculate your average speed just by dividing total distance by total time. Velocity, on the other hand, gives us the complete picture by throwing direction into the mix. It is displacement per unit time. So if either your speed or your direction changes, your velocity changes. The standard SI unit for both is meters per second. Oh, and a quick real-world tip for you. The speedometer in your car measures your speed, while the odometer measures the total distance traveled.
This next example brilliantly highlights how vectors work. Imagine a swimmer hustles to the end of a 25-meter pool and back in 50 seconds. Their average speed is their total distance, 50 meters, divided by 50 seconds, giving us a great speed of 1 meter per second. But what about their velocity? Well, because they ended up exactly where they started, their overall displacement is zero. 0 divided by 50 seconds means their average velocity is mathematically zero. All that work for zero velocity.
Okay, stepping on the gas for Section 4, understanding acceleration, the rate of change.
Now, acceleration isn't just about speeding up, which is what we usually mean when we say it. In physics, acceleration is strictly defined as the rate of change of velocity with time. And remember, because velocity includes direction, this means altering your speed or your direction counts as accelerating. If you're moving at a constant uniform velocity in a straight line, your acceleration is zero. The standard unit here is meters per second squared.
It's really interesting to see how this applies in different directions. On one hand, we have positive acceleration when a car speeds up. That positive acceleration increases the speed, but contrast that with a bus hitting the brakes. That is negative acceleration, also perfectly called retardation. Because the magnitude of the velocity is decreasing, the acceleration is actually acting opposite to the direction of motion.
Moving into Section 5, Visualizing Motion with Graphs. Seeing the invisible. Graphs are just incredibly powerful tools to visualize how distance changes with time. Take position time or distance time graphs. A straight diagonal line on a graph like this represents uniform speed, meaning equal distances are being covered in equal intervals of time. A totally horizontal line would mean the object is at rest, but the moment you see a curved line, that instantly tells us the motion is non-uniform, the object's velocity is changing, and it is actively accelerating. I really want you to remember this golden rule. The slope of a distance time graph gives you the speed of the object. It's that simple. The steeper the slope on that graph, the faster the object is actually moving in the real world. If you plot two cars on the same graph, the line that points higher up faster definitely belongs to the faster car.
Now, if we switch over to velocity time graphs, we can see exactly how velocity shifts over time. A horizontal line here indicates constant velocity. An upward slope indicates positive acceleration, and a downward slope indicates retardation. But here is the real magic trick. The slope of this graph gives you the acceleration. And amazingly, if you calculate the geometric area underneath the graph line, it gives you the exact total displacement of the object. It's like a giant puzzle fitting perfectly together.
Finally, let's dive into Section 6, the equations of motion, the universe's cheat codes.
When an object is moving in a straight line with a constant, uniformly accelerated motion, we unlock these three kinematic equations. These are beautiful, structured formulas that relate initial velocity u, final velocity v, acceleration a, time t, and displacement s. By knowing just a few of these variables, you can calculate the rest and predict exactly where an object will be or how fast it'll be going at any future time.
And hey, this isn't just theory on a chalkboard. Engineers actually use these exact equations every single day. They use them to design vehicle-to-vehicle safety systems and calculate the safe braking distance between cars on the highway. By plugging in the car's initial velocity and its braking deceleration into that third equation we just saw, they can determine the exact displacement required for that car to safely come to a complete stop.
But let's bring this right back to the real world. The math assumes a nice constant deceleration. What happens if it starts pouring rain and the road is slick, or your tires are worn down? That braking acceleration decreases dramatically. Furthermore, if you are tired, your reaction time slows down, meaning you travel way further at your initial speed before you even hit the brakes. When you think about how drastically those variables shift your safe stopping distance, you realize exactly why speed limits and following distances are absolutely crucial for survival.
Ultimately, motion forms the absolute foundation of physics. We observe it everywhere in our daily lives. Walking, running, cycling, driving, flowing rivers, rotating fans, swinging pendulums, the rotation of the Earth, and the revolution of planets. Understanding these basic concepts, distance, displacement, speed, velocity, and acceleration, doesn't just help scientists and engineers, it helps pilots, athletes, and everyday drivers. It is the vital stepping stone to studying heavier concepts like force, energy, momentum, and gravity.
I really hope this explainer empowered you to view the world a little bit differently today. Everything is connected through these elegant rules. So the next time you go for a simple walk or drive to the store, ask yourself, what is your reference point? And even if you feel completely exhausted by the end of it, what was your true mathematical displacement? Keep questioning the world around you, and thanks so much for tuning in.